All right, guys, welcome to class. We're still studying chapter 7. So today we're going to be discussing 7.2, and section 7.2 is actually focused on trigonometric integrals. Okay, so we're studying 7.2, and pretty much we have trigonometric integrals. All right. So in 7.1, we actually studied integration by parts, right? So this is slightly different in the sense that um, we're actually using, in this section, we're going to be using trigonometric identities or perhaps trigonometric substitution to actually solve integral problems. All right. So, and this brings to mind some, idea of trigonometry, which all right. So maybe from previous classes you've taken in trig before, but we're going to be using some identities, and then when we have them, I'm going to specify which identities to use. All right, so let us get started, guys. The first example I would like to talk about here. Okay, so over here, suppose you have a problem integral of sine cube of x dx. All right, so of course you might want to think for a second. All right, so let us solve this guy. So of course, I can actually rewrite this guy. This is just going to be integral, okay, sine x multiplied by sine squared x dx, right? This is fine, right? Perfect. Now, you might want to think for a second like, oh, okay, integration by parts. I can just set a part to be u, set another part to be the v, all right? So that's actually fine. It's still going to work for this problem, right? But you're going to be, doing a lot to go via that route. So that's the reason why we have the trigonometric integrals, trigonometric identities to really help you out. Okay. So what do we know previously, guys? We actually know that. So let me say, recall that when you have sine squared x plus cosine squared x actually gives you 1, right? Okay, so we're going to make this sort of substitution. This is sine squared, all right? So let me get sine squared x as the subject of the formula. So I have 1 minus cosine squared of x, right? And then at this point, I can just plug in my sine squared x. All right, so what does that mean, guys? So originally I had this problem. So I was able to split these guys into two parts. All right, so just think about it. You have a cube, a times a squared. It just gives you a cube. That's just basic law of indices. So now I want to plug in sine squared x. So this is going to be sine x. All right. So, and then I have a parenthesis 1 minus cosine squared x dx. All right. So over here now, I can think about, oh, so what next, what's the next thing I need to do? Or what's the next thing I need to worry about? All right. So you want to solve this kind of integral. What do you think, guys? Okay. So let's see if you're correct. So right now we have to think about u sub. In what sense, guys? By actually saying that let my u actually be cosine of x. Okay. So when you use cosine of x, what is du? Du is just going to be negative sine x dx, right? All right. So of course, we actually talked about u sub in section 5.5. All right. So, and then we are just applying that understanding here. Okay. So I need to write the x sub by itself. So pretty much that means I can just do dx equals du over, you have a negative sine x. And of course, if you have negative sine x on the bottom, you can just write negative du over sine x. Now, why is this important, guys? Because the moment you make a u sub, guys, you're changing variables. So if you're changing variables, you want to stick to, u, which is your new variable you just defined. Okay, so what does this mean? Pretty much it means that my sine x, all right, so this is 1 minus u squared. Remember, your u is cosine of x. So cosine squared of x is just u squared, right? U squared is just going to be cosine squared of x. But what is dx, guys? Dx is just this guy, okay? So this is going to be multiplied by negative du over sine x. Now, when you do U sub, guys, what comes to mind? Something actually cancels out, something gets simplified to make life easy, okay? So, so this guy is going to take off this guy, right? So, and then this negative sign, I can just pull it up front. So pretty much I have negative integral, okay, 1 minus u squared du. This comes back to the basic, indefinite integral. So if you want to integrate this guy, so of course you have a negative guy up front. If you integrate this guy, if you want to split up this guy, you have something like integral of du minus integral of u squared du. All right. So, the integral is an operator. So it operates on the first guy and it operates on this u squared. So that means pretty much over here I have a u minus, I'm going to have a u cubed over 3. Now, but because this is an indefinite integral, remember the constant of integration plus c, you have a plus c. Okay. So what else can I think about, guys? I can distribute by this negative sign. So, of course, it doesn't matter when you distribute. You can just distribute the negative sign from this part if you want, and then you can do it from here. So it's going to be the same. So this is u cubed over 3, all right, minus u. Of course, this is just plus c. But can we stop here, guys? Not quite, right? Because the original problem is in terms of x. So I have to stick with x. So, but what is u? U is cosine of s. So that means that my integral of sine cube of x dx is pretty much going to be 1/3. You do have a cosine cube of x, okay, minus cosine of x plus c. All right, so this becomes your answer. I hope this makes sense, guys. Okay, so sometimes when you have trigonometric integrals like this, you want to use trigonometric identities to make life easy. And what identity did we use in this case? So let me just put that guy up in red. So we know this guy, right? And then this is an equivalence. All right, so we're actually having to learn different ways and have different tools in the toolbox, so that when you want to apply them, it's pretty much going to be easy for you to come by. Okay. But sometimes we don't always have problems looking like this. Sometimes we can have a mixture of sine and cosine. So if that happens, what do we do, guys? When you have a mixture of sine and cosine, okay? So, but before we, all right, so let me just go ahead and, put that like a topic. So let me just say strategy for evaluating. All right, so if you have integrals of this sort, so you have sine, you have m right here, this is x, and this is cosine n of x dx. So if I want to evaluate this sort of integrals, what do I do? Okay, so there are some basic tips, or there are some basic steps or tricks you can apply. So number one, now remember we have integral of sine, m and n are powers, right? And they are non-zero. Okay, so let me specify in this case that m and n are different from 0. So if n is odd, and of course m and n are real numbers or natural numbers, let's stick with natural numbers. Okay, they are whole numbers. Okay, so if n is odd, now what kind of numbers are odd numbers? You can write them as 2k plus 1. Okay, so 3 is an odd number. You can write 3 as 2 times 1 plus 1, right? So if n is odd, what's the implication, guys? Okay, so let's see. So we have this guy. This is cosine So n is odd. That means I can replace n by 2k plus 1. You have x dx. Okay. So what else can I do, guys? This is just going to be all about indices at this point, guys. Just all about indices. So you have m, which is a power. You have x. Now, if you have cosine of 2k plus 1, that means 2k plus 1 is a power. I can actually rewrite that guy as cosine squared of x to the kth power multiplied by cosine of x. Okay, you can write that as this. Very trivially, guys, suppose I have p to the power of 2k plus 1. Indices tells me that this is p, this guy, times this, right, to the power of 1. And if I want to rewrite this even more, I can just do p squared to the power of k times p. And that's exactly what we just utilized right now. Okay, so this is going to be dx. But again, guys, what do we know? We know cosine squared of x. I can pull it out from my identity, right? So this is going to be integral sine mx. Cosine squared of x is exactly 1 minus sine squared of x to the power of k. You still have your k. So, and this is going to be cosine of x dx. All right. So when you simplify in this nature, what do? Now it's easy. You can just use your u sub. And in this case, what kind of u substitution do you use? You use u equals sine of x. Okay. So and then use u substitution with what? U equals sine of x. Okay. So that means whenever you have this kind of function, so let me write that in red. If you have integral, this is sine, you got mx cosine nx dx. Okay. If n is odd, the kind of u substitution you do is u equals sine x. Okay, so that's just a summary. But of course, remember that you're going to use the trigonometric identity sine squared x plus cosine squared x equals 1. So let's get into the second one. Okay, so you might have a question and saying, okay, what if m is odd? We just talked about n. What about m? Okay, so if m is odd, it's pretty much, almost the same thing, just a slight change in terms of the u sub. So my m equals 2k plus 1. Of course, this is how you write odd numbers. So I'm going to do the same analogy. This is sine 2k plus 1, right? X. Then we've got cosine n of x dx. If I want to write this guy, this is just integral of, this is sine squared x. Of course, guys, the same analogy as before. So this is sine x cosine nx dx. But what do I know? I can rewrite my sine squared of x. So this is just 1 minus cosine squared x to the power of k. This is sine x. And then you do have a cosine n of dx. Of course, n is a power, k is also a power. And those are natural numbers. All right, so, and then what kind of substitution do you do or do you use? So then use substitution with u equals cosine of x. So let me just summarize everything I've said over here. So when you're given a problem like this guy, this is sine m x cosine of nx dx. If your m is odd, what kind of u sub do you use? You use u equals cosine of x. Okay, so we're going to we're going to solve examples that actually makes you see better what we're talking about with these guys. Okay, so let's go to number 3. So in the third case, this is a situation where you have, we have case 3. If both m and n are even, If both of them are even, what do you do? So we're going to use the half angle formula, okay? Do you guys remember the half angle formulas? So you do have a sine squared x equals 1 minus cosine 2x over 2, as well as your cosine squared x equals 1 plus cosine 2x over 2. And of course, sometimes, depending on the problem, you can just use this guy, sine x cosine x equals 1 over 2 sine 2x. Okay, so these are some of the ones you can actually use. So now let's look at problems. Let's look at some examples that have this kind of mixed variation. Okay, so let's look at problems that have that sort of mixed variation. So an example is actually going to be about suppose I have integral, I have sine to the fifth power x, you have cosine squared of x dx. Okay, so this is 5, this is 2. In this case now, the 5 is an odd number, 2 is an even number. So that looks like which of the cases? Okay, that looks like case 2, right? M and N. M is odd, N is even. M is odd, that's case 2. So in case 2, what do? Keep in mind that you're going to use a substitution such as u equals cosine of x. Okay, so but what's the first thing you do? You simplify this guy, or perhaps you rewrite it in a very simpler fashion. Okay, so this is integral sine to the fifth power. You can actually break that guy down, right? Because if you have sine squared x squared, that means you have sine to the fourth power. Okay, so you have sine to the fourth power of x times sine of x, that's just sine to the fifth power. So this is cosine squared of x dx. But just like before, guys, what do I know? Keep in mind always at all times that your sine squared x plus cosine squared x is actually 1. So I can rewrite sine squared x in terms of these trigonometric identities. So this is going to be integral 1 minus cosine squared of x. You got a square here, right? So, and then you have a sine x, then you do have a cosine squared x dx. Okay, so we've gotten to a stage where we have things splitted out. So I can just say let u equals, what are we using, guys? Cosine, right? So you have cosine of x. So what is your du? Your du is exactly going to be negative sine x dx. But I need dx all by itself, right? How do I get that? So that means that my dx is going to be negative du over sine x. Looking like, a little bit of what we did in the first example we looked at some minutes ago. All right, so where do we go from here? So this is, remember, we're actually dealing with this problem. So now, where are we? So this is integral 1 minus, this is going to be a u squared, right? You have a square here. Then you have a sine x. Then you have a u squared, right? You're replacing every cosine x by u. So you have cosine squared as u squared. So what is dx? The x is negative du over sine of x. Of course, with u sub, something definitely cancels. This guy takes off this guy. So at the end of the day, I do have a negative up front, right? I have integral 1 minus u squared. You do have a square. You have a u squared du. Okay, so what do we do from here? I definitely gonna, multiply this guy twice. So if you do that, you have a negative up front. You do have an integral 1 minus 2u plus u to the fourth multiplied by u squared du. All right. So if you even multiply this guy, foil this guy, you have a negative up front. Okay, so you do have a u squared minus 2 to the 2u to the fourth power. There should be a square here, guys. Okay, so to the fourth power plus u to the sixth power, then you have a du. Amazing, guys, amazing. So now just go ahead and integrate this guy. You're going to have a negative up front. You have u cubed over 3 minus 2u to the fifth power, of course, divided by 5, and then plus u to the seventh over 7. This is an indefinite integral. You don't have any bound, maybe lower bound or upper bound. So you have a plus your constant of integration, okay, plus c. Okay, can I stop here, guys? Not quite, guys, because the left-hand side is in terms of x, the right-hand side is in terms of u. So I have to be consistent. So this is going to be equal to negative 1/3 cosine cube of x. Okay, so plus 2 to the fifth. Now, why do I have a plus? Remember, you have a negative up front, so just multiply them. So you have a cosine to the fifth power of x, and then plus cosine to the seventh power. This should be a negative, guys. Okay, because negative times positive gives you negative. 1 over 7 cosine to the seventh power of x, then plus c. Yes. So right now we're done. So you see how to handle some of these mixed, mixed things with this sort of variation, and then you can, get your solution from there. Now let's look at another example, guys. Let's look at another example. I want to evaluate this integral. I want to find this integral. This is sine to the fourth power of x dx. What do I do in this case? Now, you remember that over here, we have something like case 3, okay? So we need to play around with case 3, and then let's see what it gives us. So whenever you have this huge power, you want to break it down. Solution, so you have sine to the fourth power of x dx. This is exactly equal to, you have a sine, integral, you have sine squared x times sine squared x dx, right? If I want to rewrite this guy, this is the same thing as saying sine squared x all squared dx. So I just splitted this guy out so that you guys can see what I was trying to, to achieve. But using the half angle formula, I have an equivalence for sine squared of x, okay? So remember that sine squared of x can be written as 1 minus cosine 2x over 2. Now you might have a question saying, oh, why won't 1 over 1 minus cosine squared x work? It's not going to work because you don't have any other cosine or sine attached. So that means if you do that, you're not going to be able to solve it. So sometimes you have to make the wise decision by making the correct substitution based on, the rules or the tricks I just gave you guys above. Okay, so now we're ready to plug in this guy. This integral, let me use a black pen. So I do have an integral. This is going to be sine to the fourth power of x dx, right? That's the problem we're dealing with. So this is going to be equal to integral of, now this is sine squared x, plug in this guy, 1 minus cosine 2x over 2 all squared dx. Okay, so it's even time to multiply this guy out. If you multiply this guy out, you do have a 1/4 up front. You have an integral 1 minus 2 cosine of 2x plus cosine squared of 2x dx. How did I get this? No big deal, guys. Just do 1 minus, this is, yes, something like this. This is just 1 minus cosine of 2x divided by 2. Multiply that guy twice. If you multiply it twice, you have this right-hand side. Okay, so what else can we do from here? What else can we achieve? All right, so let me back up a little bit so that I can show you guys something. Over here we have cosine squared of x, right? If you take a look at this guy, cosine squared of x equals 1 plus cosine of 2x over 2. So we need that same ideology right here. Okay. All right. Okay, so let us do that. So let me remind you guys that cosine squared of x is actually you have a 1 plus cosine 2x over 2. But right now, over here we have cosine squared of 2x. So for that guy, I have to put a 2 here and write this guy correctly. This is going to be 2x. Okay. So what is going to happen is that these 2 is going to multiply these 2. So that way you have 1 plus cosine of 4x over 2. Okay. If that guy is 3x, then that's going to be 6x, 3 times the original 2. So now let's plug in things. Okay. So this is going to be, remember we're working with 1/4 integral of 1 minus 2 cosine of 2x. And this is going to be a plus 1/2 1 plus cosine of 4x dx. All right. So it's getting interesting, guys. So you have a 1/4. So now you have to simplify to make life easy. So you have integral 1 minus 2 cosine of 2x plus, can I split in this guy? So you have a 1/2 here plus you do have a cosine of 4x over 2 dx. So what can we do? 1 plus 1/2 gives us 3/2, right? So I have a 1/4 3 over 2 minus 2 cosine of 2x plus 1/2 of cosine of 4x dx. So right now we are ready to do the integration. Okay. If you integrate this guy, you're going to have 1/4. Open the parentheses. If you integrate 3 over 2 dx, it's going to be 3x over 2 minus, if you integrate this 2 cosine of 2x, what would it give you guys? You're definitely going to first pull out these 2. You have an integral. So let me just not, let me take it one step at a time. So plus you do have a 1/2 integral of cosine of 4x dx, right? But I hope you guys remember that when you have integral of cosine of kx dx, this is exactly going to be 1 over k sine kx plus c. So that's what I'm going to use right now. So this is going to be 1 over 4 3x over 2 minus, this is going to be 2 times 1/2 sine of 2x plus 1/2 times 1/4 sine of 4x. Of course, guys, keep in mind that you have a plus c, which is a constant of integration. Okay, so what do we do from here, guys? Can anything cancel? Definitely, guys. So this can take off this guy. So if I multiply through by 1 over 4, so I'm going to have, so that means this guy is exactly going to be 3 over 8x minus 1/4 sine of 2x plus 1 over 32 sine of 4x plus c. Interesting. Okay, because over here you have 1/2 times 1/4, that's 1 over 8. 8 times 4, you got 32, right? Interesting. Okay, so what if we have, like, a slightly different scenario? What if we do have a slightly different scenario? In that case, what do we do? Now let's consider scenarios where we're working with tangents. Okay, So when you're working with tan, so let's call this guy strategy for evaluating integral, tan to the power of m x, then you have secant of nx dx. Okay, so the first case, case one, if my n is even, what does it mean for n to be even? That means I can write n equals 2k. Even numbers are, kind of multiples of 2. You have 2, 4, 6, 8, 10, on and on. So if n is even, so I'm going to skip the simplification that I did earlier on, but it's still the same process, okay? So if n is even, what kind of substitution do you use? You use the u sub such that u equals, okay, so better still, let me write like this. So when you simplify this guy, so let me write that guy. So of course, then you simplify with, keep in mind that you do exactly the same thing we did before. In this case now, this is going to be secant squared x equals 1 plus tangent squared of x. Okay. And then use u sub with u equals tan of x in this case. We're going to see example where we can apply this. Okay. Number 2. Okay. So what if my m is odd? All right. What if my m is odd? So keep in mind, here we say n is even, here we say m is odd. What do I do, guys? So if m is odd, that means m equals 2k plus 1. I saw this earlier on. So I have to simplify with tan squared of x equals secant squared x minus 1. Okay, how do I get tan squared of x? It's exactly from this guy. Okay, it's from this guy. Just make tan squared x the subject of the formula. So remember, it's trigonometric integrals. So, and then we're using the idea of integration to be able to, idea of trigonometric identities to be able to solve our integral problem. So, and then use your u sub with, in this case, u equals secant of s. Okay, so let's pick an example. Let's do an example and let's see, how we do apply some of these principles. Okay, let me scroll down a little bit. Okay, in this case, suppose that in this case, let's have a case where both m and n are even. Okay, this is secant, fourth x. So in this case now, my m is 6, my n is 4, right? Both of them are even. What do I do? Okay, so I have to think about a way to make life easy for myself. Okay, I really have to think. Okay, so what do you guys think? Think about that for a second, and I'm going to tell you guys the answer now and see, and see what you think about it. Okay, so can we just leverage on the first trick or the first tool by keeping in mind that we're going to make some kind of substitution like, secant squared x equals 1 plus tan squared of x. All right, so let's get started. Have integral. So tan to the 6th power of x. So I'm simplifying with secant, so I have to break the secant guy down. Okay, so secant squared x times secant squared x, right? Dx. And this is just integral of tan to the 6th power of x. What is secant squared? That guy is just like tan squared x plus 1. Of course, addition is commutative. That means 1 plus 2 is the same thing as 2 plus 1. So 1 plus tan squared x is the same thing as tan squared x plus 1. So right here, I have a secant squared x dx. Okay, well, in case 1, which you're seeing above, what kind of u sub do you make? You make a sub with u equals tan of x. Okay, so let us do that. So let's u equals tan of x. So what is going to be du, guys? Du is going to be secant squared of x dx. If you differentiate tan, you have secant squared. Okay, but I need dx all by itself. So that means dx is just du over secant squared of x. Now I'm good to go. So I have to plug things in. My integral of tan to the 6th power of x secant to the 4th power of x dx is going to be integral. Remember, we said u equals tan of x. So we're back here. Let me use the red. We're plugging in stuff here. Okay. So we're plugging in stuff over there. So let's see. So you have, this is u to the 6th power, u squared plus 1, right? This is secant squared of x. What is dx? You have a du over secant squared of x. Remember, the u sub should make life easy. So take a look at this, guys. They cancel. So can you see how, it reduces to a very simple integral to work with? So this is u to the 6th, u squared plus 1 du. Okay. And then this is exactly u to the 8th power, right? Plus u to the 6th power du. So now you have a very simple integral to work with, and that gives you 1 over 9 u to the 9, right? Plus 1 over 7 u to the 7 plus c. Can I stop here, guys? Obviously not. I have to write this guy in terms of x. So that means I do have a 1 over 9. What is u? U is tan of x. So I have a tan to the 9th power of x plus 1 over 7. You have a tan to the 7th power of x. Of course, you have a plus c. So now we're done. Okay. So you see how, we can go by some of these ideas or some of this, applying with some of these principles. All right. So we have two more, around 2 more examples I would like to, or 2 to 3 more examples I'd like to discuss with you guys. All right. So before I'm done here. So another example, guys, is what if I have integral of tan to the 5th power of theta secant to the 7th power theta d theta. Okay. So this can be x, this can be theta, this can be, or t, it depends. Okay, so solution. So right now we're going to use the other trick, which is trick 2. Okay, in this case now, things are going to be slightly different. Okay, let's see. This guy says if m is odd, let's see, if m is odd, this is the kind of substitution you make. So that means I'm going to work on my tangents. So this is tan to the 5th power of theta secant to the 7th power of theta d theta integral. Can I split up this guy? This is tan, right, to the 4th power, which is, I can write it like this. Okay, so this is just a way to break down tan to the 5th power. But what do I know? I know that my tan squared theta is the same thing, guys, as secant squared theta minus 1. Okay, so this is a trigonometric identity that we're employing in this case. So right now I have tan to the 5th power of theta secant 7 theta d theta, right? Okay, so this is going to be a secant squared theta minus 1, right? Just plug it in, then you have a square here. You have a tan theta secant to the seventh power, okay, of theta. I can just also just, okay, I can break it down, but let's leave it like this for now. So what do we do, guys? What's the next thing we do? We think about the use of. Okay, so let's u equals the secant of theta. What is du, guys? When you differentiate secant, guys, do you remember what it's going to be? Okay, so this is tan theta, secant of theta, d theta. But I need d theta all by itself, d theta, because I'm switching variables. All right, so this is going to be du over tan theta, secant of theta. We're almost there, guys. The main thing is once you know how to split it down, you simplify it, you plug in the trigonometric identities, you're good. All right, so let's plug in things. I have integral. What is secant squared? This is u, right? You have u squared minus 1 all squared. Okay, so you still have your tan theta. This is secant to the 6th power theta, secant to the theta d u over tan theta secant of theta. So what do you notice, guys? I splitted up this secant 7 power, right? Because I want this guy to easily cancel this guy. And this guy is going to knock off this guy as well. So if those guys get, knocked off, what do you do? Keep in mind that, oh, we're missing something. Why do we still have a secant? We have to change this guy. So this is going to be u to the 6th power, right? Okay, so this is going to be, so now I have u squared minus 1 to the, you have a square, u to the 6th du. So guys, it's okay if you go over this video over and over again. I try to be very explanatory, but it's okay if you go over it just to, have the full grasp of what's going on. So if you expand this guy, pretty much you're gonna have u to the 10th power minus you have 2u to the 8th power, okay, plus u to the 6th du. So just multiply this guy twice and then multiply by u to the 6th power. What is this, guys? Very easy integration to handle. 1 over 11 u to the 11. Gotta have a minus 2 over 9 u to the 9th power plus 1 over 7 u to the 7th power. But remember your constant of integration plus c. Again, you cannot stop here. You have to plug in things back. What is u? Okay, so that means that my integral of tan to the 5th power theta secant to the 7th power theta d theta is just going to be 1 over 11. U was secant, right? So this is going to be secant to the power of 11. You have a theta here minus 2 over 9. You do have a secant to the 9th power of theta plus 1 over 7 secant to the 7th power of theta plus c. Okay. Amazing, guys. Amazing. Okay. Amazing. Amazing, guys. Okay. So let us see one more example, guys. One more example. Another example, guys. What if I have in this case I have integral tan cube of x dx. I can definitely do the same thing, use the same principle of splitting down this guy. This is going to be integral tan of x times tan squared of x dx. Okay, this is tan of x. But what is tan squared of x? What's in terms of trigonometric identity, you can write that guy as this. Okay, so at this point, what exactly can I do, guys? What exactly can I do? So I can multiply through by tan. Okay, if I even want to make life better, I can just multiply by tan. In that case, what happens? I'm going to have integral of tan x secant squared x dx, right? minus integral of tan of x dx. Sometimes you can have to split it in this nature because one part is easier than the other. Then you can just deal with the technical parts. All right, so over here, to deal with this guy, you have a tan and secant, right? What do? Your u sub. So let u equals tan of x. Why? Because I know that my du is going to be secant squared of x dx. When you differentiate tan, it gives you secant squared. And in the idea of, the u sub, you want something to cancel out. Okay? So this is just going to be, that guy is going to be tan cube of x dx. It's going to be integral. What is tan? U. Okay, you plug in u right here. What is this guy? You still have a secant squared x here. But what is dx? Oh, let's fix that. So du over secant squared of x, right? Du over secant squared of x. Then remember you have a minus tan of x dx. So what are we doing? We're coming from here to here. Okay. This guy knocks off this guy. So you have integral u du. Okay. If you integrate this guy, you would have ln of the absolute value of secant of x plus c. Okay. When you integrate tan x, it gives you ln of absolute value of secant of x. We're almost there, guys. What about this guy? You have a 1 over 2 u squared minus ln of secant of x plus c. But what is u? U is tan x, so I have to replace. I have to do the replacement. Thank you. X dx, which is equal to 1 over 2 tan squared x, right? Minus ln of absolute value of secant of x plus c. So, of course, these are, the very basic, ideas and identities you definitely need at some points. We've looked at about, a couple of those identities now. But if, of course, you should keep in mind that this guy, when you integrate tangents, it gives you ln of secant, right? And then when you integrate, so let me just box this out. Then when you integrate secant, it gives you ln of secant of x plus tan of x plus c. So you might definitely need these guys at some point. Okay, I hope this makes sense, guys. This is 7.2. Okay, it's a 7.2 talking about trigonometric integrals. I hope you learned something from here.